Hello everyone, in this video we're going to take a look at the electric dipole, and specifically we're going to derive the electric potential and the electric field associated with such a dipole. So to start with, let's just define what we actually mean by an electric dipole, and let's set up all of the various parameters that we're going to use in our solution. So an electric dipole is essentially just two charges of equal magnitude but opposite sign that have been slightly displaced from each other. And so that's what I've shown in this diagram over on the left here. So this blue circle at the top is a positively charged particle of charge q. So q is a positive number. And the red circle below the blue circle is a particle of charge minus q. So that's a negative number, right? And both of those particles, we've defined this this coordinate system x, y, and z here, right? The origin of the coordinate system is exactly in the middle of where those two particles are, so at the midpoint, right? And they're both lying along the z-axis. So let's define the z coordinates of our two particles. Let's put the top one at a z value of a over 2, and let's put the bottom one at a z value of minus a over 2. And so this division by 2 just makes things work out a bit more nicely, because then the separation of the particles is just a, right, rather than 2a. Okay, so we have to define a few more distances to kind of help us make some progress on this. And so firstly, I'm just going to put a little dot, let's say over here. Okay, and this is just going to be some point at which, some generic point at which we're trying to calculate the electric potential and the electric field. Okay, and so I'm going to draw a line from the origin of our coordinate system up to that point of interest, that generic point of interest, and let's call the distance of that line that I've just drawn, that's just going to be r. Okay, so that's the distance from the origin to some arbitrary point in 3D space. And I'm also going to define this angle down here, that vector that I've just drawn, so if you can imagine that as a vector, right? I'm going to define the angle that vector makes with the z-axis to be theta. Okay, so this is basically just the standard spherical polar coordinates, right? Okay, and so there are two more distances we need to define. I'm going to draw those in a slightly different color. So we can draw some more lines from each of the charged particles up to the point of interest, right? So those are those ones. And I'm going to label those, the distance from the positive particle to our point of interest is going to be called r plus, and the distance from the negatively charged particle up to the point of interest is going to be called r minus. Okay, so there we go. We've defined a bunch of parameters there, and we're also going to specify one particular approximation that we're going to make. We are going to make the assumption that basically we're looking at this dipole from a long distance away. We're going to assume mathematically, we can say that we're going to assume that the separation between the charges A is much less than the distance of our observation point from the charges, which is r. Okay, so let's get on with this derivation. And so the first thing we want to get is the electric potential, because if we know the electric potential, we can take the gradient of that to get the electric field. Okay, so let's call it V. Electric potential V. It's going to depend on r and theta, right? Those parameters of the spherical polar coordinate system that we just set up. I'm not including the other usual spherical polar coordinate, which is phi, right, the azimuthal angle, basically because of the symmetry of the problem. Okay, and so it's only going to depend on those two coordinates, r and theta, right? And we're just going to use the principle of superposition to say that we can add the electric potentials associated with each of those individual point charges, right? The dipole is just 2 point charges, and so if we add 2 point charge potentials together, the first one, the potential due to the positive charge, is going to be q over a bunch of constants, 4 pi epsilon naught, and it's going to be r plus. That's the distance to the positive charge, and we're going to have to subtract off q over 4 pi epsilon naught r minus, right, where r minus is the distance to the negative charge, and there's a minus sign here just because the charge down at the bottom there is negative, right? So its charge is minus q. Okay, so we've got these two distances, r plus and r minus, but we don't really know what they are, right, in terms of r and theta. And so that's the next thing we've got to establish. All right, so let's think about how we can write r plus and r minus. I'm going to do this as a kind of two-in-one thing, and notationally I'm just going to write r plus or minus, right? So we're going to kind of think about both of them at the same time. So r plus or minus, what's that going to be? Well, we can just use Pythagoras' theorem to say, it's going to be the square root of x squared, where x is just the x coordinate of this point of interest, right? X squared plus y squared. And then the z coordinate we have to think a bit harder about. It's not just going to be plus z squared, but if we think about the plus case first, right, the distance to the positive charge, the distance along the z-axis that we want is not just the z coordinate of that point, but it's basically this distance here that I'm marking on, right? And so, because that is the displacement along the z-axis from our point of interest to the positive charge. And so that distance is actually going to be z minus a over 2, right? And if you think about it, if we have the if we're looking for r minus instead, instead of subtracting off that little bit of distance a over 2, you're going to have to add that distance a over 2. Okay, and that whole thing is going to become squared from Pythagoras' theorem, right? So we're going to square root all of this. Let's see whether I can draw a nice straight line over the top here. Not really. Let me try again. Okay, a bit better. Okay, and now let's do a bit of algebra and see what we can do with all of this. So if we expand those squared brackets, right, we're just going to have x squared plus y squared plus z squared. Then we're going to have minus or plus twice the product of those two things in the bracketed term, right? So 2 times z times a over 2. And then we're going to get a final term, which is plus a squared over 4. Okay, so again, I've got to draw a long. That wasn't very good. Let me try one more time. Okay, fine, that'll do. So notice now that this thing here, x squared plus y squared plus z squared, has appeared. And what that is just r squared, right? Because r is just the distance from the origin to the point of interest. Okay, so we can rewrite our x squared plus y squared plus z squared as r squared. And we can also simplify this term a bit because the 2's cancel. We've multiplied by 2 and then divided by 2. And so that is just minus or plus a times z, right? And then we're going to make an approximation. We are going to ignore this a squared over 4 because we've said down here, right, that a is a small quantity relative to r. And so that is that's a second order small quantity, all right? So we're going to ignore that one. And so let's change that into an approximately equal to sign. And there we go. We've ignored a term now to make life a bit easier. Okay, so what can we do with this? Well, let's factor out this r squared. Okay, let's factor out that r squared. And then we're just going to get r in front, and we're going to get 1 minus or plus az over r squared. Right? Now, the reason for doing that is that, okay, let me rewrite this in a slightly different way. It's going to be r times the square root of 1 minus or plus. I'm going to split this second term here into a over r times z over r. Okay, because we've got an r squared, so we can do that. And then, if you think about it, z over r, we can write that in terms of theta, right? Because if you imagine a right angle triangle, I'm going to draw another line on this diagram. If you draw this kind of horizontal line so that makes a right angle with the z-axis, then if you think about this angle theta down there, we've got a right angle triangle. The hypotenuse of the triangle is r, and the adjacent side to theta is just z, right? That's the z coordinate. And so z over r is the adjacent side over the hypotenuse, which is the cosine of theta, right? So we've shown that this thing is equal to r times the square root of 1 minus or plus a cos theta. Sorry, I missed a factor of r, didn't I? So it's going to be a cos theta divided by r. Okay. Now, what we can do is make another approximation, okay? Because a over r, this second term here is a cos theta over r, which is linear in a over r, but a over r is much less than 1, right? That's what we said at the beginning. And so we could do a binomial expansion on this whole thing and just do it to first order in a over r. And so if we do that, we are going to get r times, well, basically what we've got is 1 minus or plus a cos theta over r raised to the power of a half. Okay, and so what we do is just bring down that factor of a half. We get 1 plus, sorry, minus or plus half of a cos theta over r. So that's just doing a first order binomial expansion on that thing over there. Right, so we now know r plus and r minus in terms of r and theta. So let's plug those back into our expression for v of r and theta. So v of r and theta, remember that was what we wrote at the top there, okay? It's going to have a common factor. If you look at those two terms, it's going to have a common factor of q over 4 pi epsilon naught r, right? Because r plus and r minus, they both have a prefactor of r. So we can take that r out. And then the first term, we're going to get 1 over 1 minus half a cos theta over r. The second term, we're subtracting 1 over the same thing but with a plus sign. So 1 plus half a cos theta over r. Okay, a cos theta over r. Right, we're going to make yet another approximation. We can do some more binomial expansions, right? Because 1 over something is the same as that thing raised to the power of minus 1. Okay, and so what that means is, let me just write this prefactor, q over 4 pi epsilon r. This whole thing here, this first term, 1 over 1 minus a half a cos theta over r, that is the same to first order in a over r. That's the same as 1 plus half a cos theta over r. Because basically what we had was, well, 1 minus a half a cos theta over r to the power of minus 1. And so if we do a first order expansion, that minus 1 comes down and multiplies with that minus sign and turns it positive, right? And so, yes, this entire first term approximates to this, to first order. And so we should, this should also be approximately equal to, right? And then we're going to subtract off a similar thing for the second term, except again, because basically we've got this whole thing to the power of minus 1, if we do a binomial expansion, that just flips the sign in the middle here. And so we subtract off 1 minus half a cos theta over r, right? Okay, so notice that the 1's cancel. That 1 cancels with that 1. And then these two terms are the same, right? And because each of them has a half as a prefactor, the halves basically just cancel, right? We add two halves together and we get a whole. And so we have found that our electric potential is roughly qa cos theta, so q times a cos theta over 4 pi epsilon naught r squared. I'm just going to make one more definition here. I'm going to say, introduce the quantity p, which is called the dipole moment. I'm going to say the dipole moment p is defined to be the charge q times the separation a, right? And so you'll often see this dipole potential written in the form p cos theta divided by 4 pi epsilon naught r squared. So we now have an expression for the electric potential of a dipole under the approximation that we're viewing it from a long distance away. And that was this thing up here, p cos theta over 4 pi epsilon r squared. Let's use that to get the electric field, right? We can do that fairly straightforwardly because the electric field, E, which is a vector, is minus the gradient of the electric potential, okay? And so let's just put a minus sign there. The gradient in spherical polar coordinates, which is what we're working in, right? This r and theta. Gradient in spherical polar coordinates, we get a contribution of dv by dr in the r unit vector direction. And then we get a 1 over r dv by d theta in the theta unit vector direction. Okay, so when you're working in non-Cartesian coordinate systems, you get things like this 1 over r starting to appear, which is basically because the basis vectors are varying with position themselves, right? And remember that the third spherical polar coordinate phi we don't get a component in that direction here because dv by d phi is 0. Okay, so we've just got two partial derivatives to evaluate basically. So that electric field is going to be minus. So if we just take this thing at the top, differentiate with respect to r, we've got r to the minus 2, okay, because it's r squared on the bottom. So we pull down a factor of minus 2, so we get minus 2 p cos theta, and then the r squared on the bottom turns into an r cubed. So that's all multiplied by the r hat vector. And then what we have is, mustn't forget our 1 over r. Then we just differentiate our potential with respect to theta. Cos theta turns into minus sine theta. And so we get minus p sine theta divided by 4 pi epsilon naught r squared. Okay. Oh, and that's in the theta hat direction, right? So let's write out a final expression here. This is, oh, by the way, this should all, well, from this stage here, this should be an approximately equal sign, right? Because this is only valid when r is much bigger than a. And so, yeah, this is approximately equal to p over, let's pull out a common factor, of p over 4 pi epsilon naught r cubed, right? Remember, this theta hat term also really has an r cubed on the bottom because there's an r there and an r squared there. So we can pull out that common factor, and then the r hat component is going to be 2 cos theta, and the theta hat component is going to be just sine theta. Okay. And so we can just check that this kind of makes sense by plugging in a few values of theta. For example, if we consider the case when theta is 0, in other words, when theta is 0, we're along the z-axis, right? So somewhere along the z-axis. If theta is 0, we find that this sine theta term disappears, and the electric field is purely in the radial direction. But when we're along the z-axis, this radial direction is itself along the z-axis, and so in other words, when you're along the axis of the dipole, the electric field is pointing purely along that axis, which kind of makes sense. It's what we would expect from the symmetry of the problem, right? And we can also plug in theta is pi over 2. That's a fairly simple value to interpret, because if theta is pi over 2, all that means is you are in the xy plane somewhere, okay? Now, mathematically, if theta is pi over 2, this time the cos theta term disappears, and we find the electric field is purely in the theta hat direction. But when you're in the xy plane, the theta hat direction is pointing straight downwards, is pointing in the minus z direction, okay? And so what that means is in the xy plane, the electric field is pointing purely vertically downwards from the direction, in the direction going from the positive charge to the negative charge, which again is kind of what we would expect from the symmetry of the problem. So there you go. We've derived expressions, approximate expressions for the potential and electric field of a dipole.